The universe hides an object that should not exist. It is a cosmic paradox, a place where gravity seems to win, but physics whispers a different story. We call these places black holes, but what if everything we think we know about them is wrong? Today we explore a radical idea, a theoretical object known as a gravastar. By the end, you will understand a compelling alternative that could rewrite the rules of stellar death. We will uncover how it might solve black holes' greatest mysteries and what strange substance at its heart could be pushing the entire cosmos apart. What does it feel like to question the foundations of reality itself? The heart of a black hole is a point of infinite density, a mathematical breakdown called a singularity. Surrounding it is the event horizon, a boundary of no return. Once anything crosses this invisible line, not even light can escape its gravitational pull. This is the classic picture painted by Einstein's theory of general relativity. We see their influence across the cosmos, from the brilliant, swirling disks of superheated gas that feed them, to the way they warp the very fabric of space-time, bending light from distant stars like a cosmic lens. Yet for all their power, black holes present profound puzzles. The singularity is where our laws of physics simply stop working, and the event horizon creates the infamous information paradox, where anything that falls in seems to be erased from the universe forever. These are not just small gaps in our knowledge, they are screaming contradictions at the core of modern physics. It is precisely these paradoxes that drive scientists to ask a daring question: what if the universe found a more elegant solution? What if the collapse of a massive star does not create a bottomless pit, but something entirely new and strange instead? These screaming contradictions are more than just theoretical headaches. They are fundamental glitches in our understanding of reality. The singularity, that point of infinite density at the center of a black hole, is a sign that our mathematics have broken down. In the real world, nothing can truly be infinite. It is a placeholder, a mathematical confession that our equations do not know what happens when gravity becomes that strong. This is not just a tiny gap in the map, it is a tear in the fabric of physics itself. Then there is the information loss paradox. According to quantum mechanics, information about the state of a particle, its spin, its charge, its identity, can never be truly destroyed. It might get scrambled beyond recognition, but it must, in principle, be preserved. A black hole's event horizon seems to violate this sacred rule. When matter falls in, that information appears to vanish forever, trapped behind a one-way curtain. This creates a direct conflict between the two pillars of modern physics, Einstein's general relativity and quantum theory. One says information is lost, the other says it cannot be. They cannot both be right. These paradoxes are not problems we can ignore. They are clues, bright flashing signs that our picture of a black hole, for all its predictive power, might be incomplete. They force us to ask, what if the universe has a more clever, more stable way to handle the death of a star? What if the collapse does not end in a meaningless infinity, but transforms into something else entirely, something that resolves these paradoxes at their core? This is the powerful motivation for imagining an object like a gravastar. It is not born from a desire to replace Einstein, but from a need to complete the picture, to find a cosmic solution that respects all the laws of physics. This is where the gravastar enters the stage, a radical proposal born from the very need to solve these paradoxes. Coined by physicists Paul Mazur and Emil Matola, the gravastar is not a black hole at all, but something entirely different that could masquerade as one. It is a hypothetical object designed from the ground up to have no singularity and no true event horizon. Instead of a point of infinite density, its core is theorized to be a bubble of exotic quantum vacuum, a strange state of space itself that exerts a powerful outward pressure. Think of it not as a bottomless pit, but as a cosmic egg with an incredibly dense, exotic shell surrounding a hollow interior of repulsive energy. This single idea elegantly sidesteps the greatest headaches of black hole physics. No singularity means no breakdown of physical laws, and without a true point of no return, the information paradox might simply vanish because information would never be trapped forever behind an uncrossable barrier. The gravastar presents itself as a bold, clean solution, a cosmic structure that could explain all the gravitational pull we observe from the outside while offering a stable, paradox-free interior. It is a testament to human ingenuity, an attempt to rewrite the final chapter of a star's life with a more complete and perhaps more beautiful set of physical rules. The structure of a gravastar is a universe away from the dark simplicity of a black hole. Picture a cosmic onion, but one with just two incredible layers, each defying our everyday experience. At its very center, instead of a crushing singularity, there is a hollow sphere. This is not empty space, however. It is filled with a bizarre substance known as a Bose-Einstein condensate, a superfluid form of dark energy. Think of it as space itself, cooled down to its absolute lowest possible energy state, becoming a single, coherent quantum field. This exotic core exerts a tremendous repulsive pressure, pushing outward against the immense force of gravity. It is this pressure that prevents total collapse and banishes the singularity forever. Containing this strange heart is the gravastar's second layer, a shell of unimaginable density. This crust is not made of exotic energy, but of ordinary matter, atoms and particles compressed to a state beyond anything we can create. It is this ultra-dense shell that creates the immense gravitational pull we would observe from the outside, mimicking the grip of a black hole's event horizon. Yet it is not a true point of no return. The shell has a finite, though extraordinary, thickness, so while crossing it would be catastrophic for any spacecraft, in theory, information is not lost forever behind an absolute barrier. This elegant, layered architecture offers a complete alternative, replacing the terrifying void of a black hole with a stable, structured object where physics remains intact from its exotic core to its dense, glittering surface. This bizarre core is the gravastar's greatest mystery and its most revolutionary idea. We are talking about a hollow sphere filled with dark energy, the same mysterious force that is causing the entire universe to expand at an ever-increasing rate. To understand how this could be inside a star, we need to rethink what dark energy is. In the simplest terms, think of empty space not as nothing, but as a seething quantum field with its own intrinsic energy. This energy exerts a negative pressure, a kind of repulsive gravity that pushes space itself apart. Now, imagine that same expansive force, not spread thinly across the cosmos, but trapped and concentrated within the shell of a collapsed star. It creates a balance of cosmic proportions. On one side, you have the crushing inward pull of gravity from all that collapsed matter in the shell. On the other, you have this immense outward push from the dark energy core. They reach a stalemate, a perfect equilibrium that prevents the final, catastrophic collapse into a singularity. This core is not a place of matter, but a place where space itself has undergone a phase transition, like water freezing into ice, becoming a Bose-Einstein condensate. It is a single, coherent quantum state that acts as a cosmic shock absorber, forever pushing back against the weight of the universe. The profound connection here is staggering. The same force that governs the large-scale fate of everything, the acceleration of galaxies away from each other, might also be the secret ingredient that stabilizes the graves of the most massive stars. It suggests a beautiful symmetry where the physics of the unimaginably large and the incomprehensibly dense are woven from the same strange fabric. This shell is the ultimate cosmic barrier, a wall of matter so dense it approaches the fundamental limits of reality itself. We are talking about Planck density, a number so vast it borders on the meaningless. To grasp it, consider that a single cubic centimeter of this shell material, a space smaller than a sugar cube, would contain a mass greater than our entire observable universe. It is a density where the very concepts of space and time as we know them begin to blur and break down. This is not a shell of rock or metal, but a crust of fundamental particles, likely quarks and gluons, compressed into a state of matter that has no name, a formless, ultra-dense soup held together by the sheer force of gravity pressing inward and the dark energy core pushing outward. Its purpose is monumental, to act as the definitive boundary between two completely different phases of the cosmos. On our side, the universe governed by the familiar laws of physics. On the other side, that hollow interior filled with the exotic Bose-Einstein condensate. This shell prevents the two from mixing, maintaining a stable, if unimaginably tense, equilibrium. Most critically, it is this finite, physical barrier that stops a true event horizon from ever forming. There is no mathematical point of no return, only a region of such extreme gravity that escaping it would require near impossible energy. But because the shell has a thickness, however minuscule, the door is not permanently sealed shut in principle. Information is not erased, it is merely trapped behind a wall of staggering but not infinite density. The Gravastar's shell is not a curtain closing on reality, but the most formidable locked door in the universe, one that might, just might, still have a key. From the outside, the universe would struggle to tell them apart. A gravastar and a black hole would both appear as perfect spheres of absolute darkness, warping the fabric of space-time with a gravitational grip so fierce they bend light into glowing rings and pull stars into frantic orbits. Any telescope pointed at the center of our galaxy, at the object we call Sagittarius, a star, would see the same violent ballet of superheated gas and twisted starlight, regardless of which monster truly lurked there. This cosmic mimicry is the Gravastar's greatest strength and our greatest challenge, for it was designed to explain all the gravitational phenomena we already observe. Yet, if they are truly different beasts at their core, there must be subtle cracks in the disguise, tiny observational signatures that could betray the truth. The most critical difference lies in that boundary of no return. A black hole possesses a true event horizon, a mathematical surface from which nothing, not even a single photon of light, can ever escape. It is a one-way door that permanently severs information from our universe. A gravastar, however, has only an ultra-dense shell. While crossing it would be fatal, it is not a perfect, timeless barrier. In theory, this could lead to faint but detectable differences. For instance, matter from the accretion disk, that swirling whirlpool of doomed gas, would not simply vanish as it approaches the surface of a gravastar. Instead of being silently swallowed by an event horizon, it would strike that physical crust. The collision would be unimaginably violent, potentially releasing a final, distinctive flash or a burst of particles just before assimilation, a last signal that something solid was struck. Furthermore, the absence of a true event horizon might influence the very ring of light we see, the photon sphere. The subtle way light echoes and lenses around the object could carry a unique fingerprint, a signature of a surface versus an abyss. Perhaps the most promising clue lies in gravitational waves, the ripples in space-time sent out by colossal cosmic events. When two black holes spiral together and merge, their event horizons dance and finally coalesce in a specific, predictable pattern, creating a characteristic chirp signal. The merger of two gravastars with their dense physical shells would be a vastly different process. Their shells would resist and vibrate, potentially ringing like unimaginably dense bells during collision, sending out a distorted gravitational wave song that our observatories like LIGO and Virgo might one day distinguish from the clean tone of a black hole merger. Finding that distortion in the cosmic hum would be the smoking gun, proof that what we thought were bottomless pits are actually structured objects, cosmic eggs with shells of incredible density. The hunt is on for these ghostly echoes, for the tiny deviations in light and gravity that could reveal whether the darkest spots in our sky are truly eternal prisons or the most brilliant disguises in the universe. This potential for a final signal before impact is more than a quirk. It is a direct assault on the black hole's most famous paradox. The information loss problem melts away when you replace an event horizon with a physical surface. In a black hole, information crosses that mathematical boundary and is, for all intents and purposes, erased from our universe, violating a core rule of quantum mechanics. But a gravastar offers a different fate. When matter and energy strike that ultra-dense shell, they are not swallowed by a one-way curtain. They are annihilated, transformed, and assimilated into the shell itself. The information they carry, the unique quantum states of every particle, does not vanish. It is imprinted onto the state of the shell in an incredibly complex, scrambled form. Much like the information in a book is not destroyed when you burn it, it is merely transformed into heat, light, and ash. The information is still present in the universe, just in a form that is, for now, practically impossible for us to decode. This preservation satisfies the fundamental quantum law that information must be conserved. There is no paradox because there is no point of no return. The door is locked, but the room still exists inside the house of the universe. Furthermore, this model allows for a fascinating possibility: leakage. Over astronomical timescales, through quantum processes like Hawking radiation, which a gravastar would also emit, that scrambled information could theoretically be slowly radiated back out into the cosmos. It would be like trying to reconstruct a burned book from the pattern of smoke and the warmth of the ashes, an unimaginable task but a physically possible one. The gravastar does not trap information forever. It encrypts it on the most secure hard drive in existence, one that might, over eons, allow for a cosmic data recovery. This elegant resolution turns a screaming contradiction between gravity and quantum theory into a complex but solvable engineering problem of physics. But this preservation of information comes with its own terrifying price in the standard black hole model, a price so severe it is known as the firewall paradox. Imagine you are an astronaut foolishly falling feet first toward a black hole's event horizon. According to Einstein's principle of equivalence, you should feel nothing special as you cross that invisible line. Space-time should be smooth, and you will be blissfully unaware of your point of no return, at least for a little while. This is the no-drama prediction of classical physics. Yet, quantum mechanics paints a horrifyingly different picture. To preserve information and allow it to eventually leak out as Hawking radiation, quantum theory suggests that the event horizon cannot be a calm place. Instead, it must be a seething, energetic barrier, a literal wall of ultra-high energy particles. For information to escape, the horizon must encode it, and that encoding process would turn the boundary into a blazing inferno of quantum chaos. An astronaut crossing it would be instantly incinerated by this firewall. So we are left with an impossible choice. Either Einstein is wrong and the event horizon is a violent, fiery death trap which breaks the smooth geometry of space-time, or quantum mechanics is wrong and information is lost forever, breaking a fundamental law of the universe. It is another brutal conflict between our two best theories of reality. A gravastar dissolves this paradox before it can even form, simply by removing the ingredient that causes it, the event horizon itself. There is no sharp, mathematical boundary of no return. Instead, there is a physical shell of incredible but finite density. The transition from the outside universe to the interior is not an instantaneous jump over a line, but a journey through a region of extreme yet smooth space-time curvature. An astronaut approaching a gravastar would not encounter a sudden wall of fire. They would experience gravity growing stronger and stronger, space stretching and warping in a continuous gradient. The immense tidal forces near the shell would still tear any object apart long before it reached the surface, but this is a classical effect of extreme gravity, not a paradoxical quantum firewall. The information paradox is handled by the assimilation of matter into the shell, and without an event horizon, there is no need for that information to be encoded in a violent, energetic barrier. The spacetime geometry around and within a gravastar can remain smooth, respecting Einstein's vision, while still finding a way to preserve quantum information within the structure of its dense crust. It offers a path where both great theories can be right, where the drama of physics plays out not on a burning horizon, but within the stable, layered architecture of a new kind of celestial object. Building a stable model of a gravastar requires stitching together two separate worlds of physics, a task that pushes our mathematical tools to their absolute limit. On one hand, we have the grand geometric vision of Einstein's general relativity, which describes gravity as the curvature of space-time itself. Its equations tell us how matter and energy warp the cosmic fabric. To model the immense gravitational pull of the gravastar's shell and the smooth, warped space around it, we must solve these equations under extreme conditions. But Einstein's theory alone cannot create the gravastar's exotic core. For that, we must dive into the bizarre, probabilistic realm of quantum field theory, the framework that describes particles and forces as excitations in underlying fields. The key innovation is applying quantum field theory not to flat, empty space, but to the highly curved, dynamic space-time geometry created by the shell's gravity. This is the challenging domain of quantum field theory in curved space-time. Here, the vacuum, what we think of as empty space, is no longer simple. In the intense gravitational field near the gravastar, the vacuum becomes active, seething with virtual particles and possessing a tangible energy. This is where the magic happens, through a process called gravitational vacuum condensation. Think of it like this: imagine taking the air in a room and cooling it down further and further. At a certain critical temperature, the water vapor in the air will condense into liquid droplets on a cold window. In a similar but far more exotic way, the intense gravitational pressure and the curved space-time around a collapsing star are thought to act like that critical cooling point. They force the quantum vacuum itself to undergo a phase transition, condensing from its normal high-energy state into that superfluid, low-energy Bose-Einstein condensate that fills the gravastar's interior. This condensate is not a substance you could touch. It is a new state of space itself, a region where the quantum fields have settled into their absolute lowest energy configuration, and in doing so, they generate that powerful, repulsive dark energy pressure. Modeling this is the ultimate balancing act, using Einstein's equations to describe the curved space caused by the shell, and then using quantum theory to show how that curved space, in turn, transforms the vacuum into the stabilizing core. It is a delicate, self-consistent loop of cause and effect where gravity creates the conditions for its own limitation, a mathematical dance that, if correct, would be one of the most elegant solutions in all of theoretical physics. Yet this elegant mathematical dance faces its greatest test, the relentless force of gravity itself. The central question is not just whether gravastars can exist in theory, but whether they can survive for more than a fleeting moment. Can that delicate balance between an outward-pushing dark energy core and an inward-crushing shell of matter truly hold? Or would such a structure inevitably collapse into a black hole or violently explode, vanishing in a cosmic instant? This is the stability problem, and it is the most serious criticism leveled against the gravastar model. Think of it like building a dome out of impossibly heavy stones, with nothing but a constant, powerful updraft of air holding them aloft. The slightest imbalance, the tiniest fluctuation in pressure or density, and the entire structure would come crashing down. For a gravastar, the shell must be perfectly uniform and under immense tension. Any perturbation, like a large asteroid impact or even the inherent quantum jitter of the particles within the shell, could trigger a catastrophic instability. The shell might start to oscillate with waves of density rippling across its surface. If these oscillations grow instead of dampening out, they could cause the shell to either buckle inward, allowing gravity to finally win and crush the core into a singularity, or rupture outward, releasing the pent-up dark energy in a titanic burst. Theoretical studies have explored this from every angle. Some complex mathematical models suggest that under very specific, finely tuned conditions, certain types of gravastars could achieve a stable equilibrium. They propose that the exotic matter in the shell might have unusual properties like negative energy densities that act as a form of cosmic glue, reinforcing the structure against small disturbances. Other studies, however, are far less optimistic. They show that for many plausible models, the stable configuration is like a pencil balanced perfectly on its tip, a mathematical possibility that any real-world vibration would instantly destroy. The shell is simply too thin, the pressures too extreme, and the margin for error too non-existent. Critics argue that in the chaotic aftermath of a supernova, as a star's core collapses, the process would be far too messy and violent to arrange itself into such a precarious, perfect layered object. It would be like expecting a collapsing building to spontaneously form a perfect, hollow bubble as it falls. The natural tendency, they say, is for gravity to take the simplest, most direct path, crushing everything into a point. So the debate continues in the realm of equations and supercomputer simulations. The dream of a stable gravastar is a fight against entropy and chaos, a battle to see if the universe allows for such a perfectly engineered cosmic artifact, or if nature always chooses the simpler, darker path. The quest to replace the black hole does not end with the gravastar. It is part of a broader, more daring search for stable alternatives, other cosmic objects that could wear the same gravitational disguise. Among these, two other theoretical proposals stand out, each built from a different kind of cosmic exoticism. First, consider the boson star. Unlike a star made of atoms, a boson star would be a giant, diffuse sphere composed entirely of a theoretical type of particle known as a scalar field. Think of it not as a ball of fire, but as a shimmering, coherent quantum wave held together by its own gravitational attraction. These particles, if they exist, could avoid the crushing fate of normal matter because of their quantum properties, allowing them to form a stable, gigantic object without ever collapsing to a singularity. They are ghostly halos of pure force, potentially mimicking a black hole's shadow. Then there is the even more speculative dark star. This object would form in the early universe, not from regular gas and dust, but from a dense cloud of dark matter. Its power source would be utterly alien, not nuclear fusion, but the mutual annihilation of dark matter particles at its core. This process would release enough energy to keep the star puffed up against gravity for eons, a faint, cool giant glowing with the heat of annihilating shadows. Both of these ideas, like the gravastar, seek to explain dark, massive objects without invoking a point of infinite density. Yet the gravastar carves out its own unique niche. While boson stars are made of exotic particles and dark stars are powered by them, the gravastar's revolutionary heart is not made of matter at all. Its core is a phase of space itself, a bubble of repulsive vacuum energy. This is a profound distinction. It suggests that the most extreme objects in the universe might not be made of strange stuff, but might instead be places where the very fabric of reality undergoes a transformation. The gravastar is not just an alternative compact object, it is a proposal that the vacuum of space under enough pressure can become the ultimate structural element, holding back the weight of a dead star with nothing but its own inherent push. This places it in a category of one, a cosmic object where the emptiness inside is the most important part of its design. But the implications of such a strange object might reach far beyond solving black hole puzzles. They could touch on one of the greatest mysteries in all of cosmology, the nature of dark matter. This invisible substance, which outweighs all the stars and galaxies we see by a factor of 5, has only revealed itself through its gravitational pull. We know it is there, but we have no idea what it is made of. Could gravastars or objects like them be a piece of that cosmic puzzle? It is a speculative but thrilling possibility. For gravastars to explain even a fraction of dark matter, they would need to exist in vast numbers, scattered throughout the halos of galaxies, including our own Milky Way. They would need to be completely dark, emitting no light, and stable over the entire age of the universe. And crucially, their mass would have to fall into a very specific range. They could not be the supermassive monsters we find at galactic centers, weighing millions of suns. Instead, they would need to be far smaller and more numerous, perhaps with masses ranging from that of a large asteroid to several times the mass of our Sun. These would be primordial gravastars, not born from the death of individual stars, but forged in the unimaginable heat and density of the Big Bang itself. In the first chaotic moments of the universe, as space-time rapidly expanded and cooled, tiny fluctuations in the quantum fields could have triggered pockets of vacuum to undergo that critical phase transition, condensing into stable bubbles of dark energy surrounded by thin, ultra-dense shells. These primordial gravastars would have formed before the first stars ever ignited, becoming fossil relics of the universe's explosive birth. If they formed in sufficient abundance, they could now be drifting unseen through the vast spaces between stars, their collective gravitational influence subtly guiding the rotation of galaxies and the bending of light from distant objects, exactly as dark matter is observed to do. The elegance is compelling. One exotic theoretical object could solve two of astrophysics' biggest problems: the paradox of black holes and the identity of the universe's hidden mass. Yet, the leap from a neat idea to a proven component of reality is enormous. We have no direct evidence that such primordial gravastars formed, or that they could survive for 14 billion years. Their proposed mass range also puts them in a category that is notoriously difficult to detect: too light to significantly distort light from a single background star like a black hole would, yet too heavy to be found by other means. They would be cosmic ghosts felt but never seen. So while the connection to dark matter remains a captivating what if, it underscores a deeper truth: the search for alternatives to black holes is not just about rewriting the end of a star's life. It is about questioning the fundamental ingredients of our cosmos and realizing that the darkest places in the universe might hold the keys to its lightest secrets. The birth of a gravastar would be the ultimate cosmic metamorphosis, a stellar death that refuses to end in darkness. It begins with the same catastrophic event that creates a black hole: the collapse of a massive star's core. After burning through its nuclear fuel, the star can no longer support its own immense weight. Its heart gives out and gravity, the patient sculptor of the cosmos, seizes absolute control. The core implodes inward at a significant fraction of the speed of light, crushing matter to densities beyond comprehension. But here, at the very precipice of oblivion, the gravastar story diverges. In the standard tale, nothing can stop this collapse and a singularity forms. In the gravastar hypothesis, something does stop it, not a new force, but a profound change in the very nature of space itself. As matter is compressed beyond the density of an atomic nucleus, we enter a realm where quantum mechanics, not just gravity, dictates the rules. The empty space between particles, the quantum vacuum, is no longer a passive backdrop. Under this unimaginable pressure, it becomes an active participant. Think of it like squeezing a sponge soaked in water. Initially, you just compress the sponge. But past a certain point, you begin to squeeze the water out. In this cosmic analogy, the collapsing matter is the sponge, and the water is the latent energy of the vacuum. At a critical threshold of density and curvature, a phase transition is triggered. the quantum vacuum inside the collapsing core undergoes a sudden, radical shift. It condenses like steam cooling into water droplets, transforming from its normal high-energy state into that exotic, low-energy Bose-Einstein condensate. This new state of space possesses a powerful negative pressure, a repulsive force that acts like cosmic antigravity. Just as the core is about to crush itself out of existence, this vacuum pressure switches on, pushing outward with tremendous force. It slams against the inward rush of collapsing matter, bringing the implosion to a sudden, violent halt. The infalling material, now frozen in this impossible balance, forms the ultra-dense shell. The interior, now a bubble of transformed vacuum, becomes the dark energy heart. In a flash of cosmic alchemy, a collapsing star does not become a hole in reality, but a structured object, a gravastar, where the emptiness inside is its most vital organ. This formation process suggests a universe that is inherently stable, finding elegant quantum solutions to avoid its own mathematical breakdowns, turning potential graves into eggs of strange new physics. But even a structure as seemingly eternal as a gravastar must face its own end. If black holes can slowly evaporate through Hawking radiation, what fate awaits their theoretical rival? The answer hinges on the very nature of that ultra-dense shell. Hawking radiation arises from quantum effects right at the event horizon, where pairs of virtual particles pop into existence. Normally, they annihilate each other instantly, but if one particle falls across the horizon while the other escapes, the black hole loses a tiny amount of mass. For a gravastar, there is no true event horizon, but there is still an intense gravitational field and a physical surface. Quantum fields would still fluctuate wildly near this boundary, meaning a similar process of particle creation should occur. The shell would absorb one particle from a pair while the other radiates away, carrying energy. This suggests gravastars would also slowly lose mass over time, evaporating in a process analogous to, but likely different in detail from, Hawking radiation. However, the presence of a surface changes everything. The evaporation would not be a clean, featureless leak from a void. As the shell loses mass, the delicate balance between its inward crush and the dark energy core's outward push would be disturbed. The core's repulsive pressure would begin to dominate, causing the entire structure to expand ever so slightly. We might picture a gravastar not simply shrinking, but slowly inflating as it evaporates, its shell becoming thinner and less dense over eons. This leads to a fascinating and unresolved question: what happens when the shell becomes too thin? One possibility is a phase transition in reverse. As the shell's mass evaporates away, the pressure confining the dark energy core weakens. The exotic vacuum inside might suddenly revert to its normal state, like ice melting back into water. This would release the pent-up repulsive energy in a final, catastrophic event. A burst of radiation and particles that would mark the gravastar's true death, transforming it back into ordinary, expanding space. Another, more speculative end could be a quantum tunneling event, where the entire structure spontaneously decays into something else entirely. The life cycle of a gravastar, from its violent birth in a collapsing star to its possible slow evaporation and final transformation, remains one of the greatest open puzzles. It forces us to ask what eternity really means for a cosmic object, and whether anything, even a perfect balance of forces, can truly last forever. The final moments of a gravastar's life, whether through evaporation or a cataclysmic merger, would send ripples through the very fabric of space-time. These gravitational waves are not just cosmic echoes, they are our most promising chance to finally tell a black hole from its exotic twin. When two black holes spiral together and merge, their event horizons dance and coalesce in a very specific way, producing a gravitational wave signal with a clean, predictable fingerprint. It begins with a rising chirp as they spiral inward, peaks in a violent burst as they collide, and then fades away in a rapid, smooth ring down as the new, larger black hole settles into a quiet, perfect sphere. This ring down is the signature of a featureless object, a pure pit in space-time with no internal structure to vibrate. A gravastar merger would tell a completely different story. The moment their ultra-dense physical shells touch, the event would be far messier. Instead of two featureless horizons merging, you would have two incredibly rigid structures colliding. The shells would not simply vanish into a new horizon. They would shatter, vibrate, and resonate against each other and against the repulsive dark energy cores trapped within. This would distort the gravitational wave signal in two key ways. First, the final, peak burst of the collision would be less clean and sharp. Second, and most importantly, the ring down would not be smooth and rapid. Instead of fading away quickly, the signal would show prolonged, dampening oscillations like the ringing of a bell after it has been struck. These are the gravitational wave echoes. The newly formed, larger gravastar would not be a perfect sphere immediately. Its shell would be wobbling and vibrating as it seeks a new equilibrium, sending out additional faint pulses of gravitational waves in the seconds or minutes following the main collision. For instruments like LIGO and Virgo, listening for these echoes is like trying to hear the distinct reverberation inside a metal bell instead of the dull thud of a stone dropped into a deep well. It is a subtle difference buried in immense noise, but it is a difference that physics demands. Finding that telltale ring would be the smoking gun, proof that what merged were not pure voids, but objects with a surface, a structure, and a secret heart of dark energy. The Event Horizon Telescope gave us our first direct glimpse into the abyss. Its historic images revealed not a black hole itself, but its dark silhouette, the shadow cast against the glowing ring of superheated gas swirling around it. For M87 star and Sagittarius A star, this shadow matched the predictions for a black hole's event horizon with stunning precision. But does this shadow prove a black hole exists, or could it also be the silhouette of a gravastar's ultra-dense shell? The answer is a fascinating and contentious maybe. The shadow we see is not a picture of the event horizon. It is a complex pattern of light bending called a photon ring, created by the object's immense gravity. Both a black hole and a gravastar, if they are massive and compact enough, would warp space-time in an almost identical way from our distant vantage point. Their gravitational lenses would be nearly indistinguishable, producing a shadow of the same size and shape. The key word is nearly. The subtle differences lie in the fine details of that glowing ring of light. A black hole with its true event horizon would have a perfectly clean, sharp inner edge to its shadow. A gravastar with a physical surface might show a slightly different signature. Light rays that skim the surface could interact with it in minute ways, perhaps creating a faint, additional ring of light just inside the main shadow's edge, or causing subtle asymmetries in the brightness of the ring itself. The current images from the Event Horizon Telescope are monumental achievements, but they are at the very limit of our resolution. They are like the first blurry photograph of a distant mountain. We can see its outline clearly, but we cannot yet make out the texture of the rock or see if there is a fence partway up the slope. The data so far is beautifully consistent with a black hole, but it does not yet rule out a gravastar or other exotic compact objects. The debate in the astrophysics community is alive and vigorous. Some researchers are actively searching through the Event Horizon Telescope data for those tiny anomalies, those ghostly echoes of a surface. Others are running sophisticated simulations to predict exactly what a gravastar's shadow should look like under different conditions. The next generation of the telescope, adding more observatories around the globe and observing at even higher frequencies, aims to sharpen that picture from a blurry snapshot into a high-resolution portrait. It will peer closer to the edge of the shadow, searching for the telltale fingerprints of a physical boundary. Until then, the shadow remains a cosmic Rorschach test. We all see the darkness, but what we believe lies within it depends on which equations we trust more. This quest for a surface is more than a hunt for one exotic object. It is a direct assault on the deepest problem in all of physics. The paradoxes of black holes and the very design of gravastars point to a fundamental schism in our understanding of reality. On one side stands Einstein's general relativity, the theory of the very large, where gravity is the graceful curvature of space-time. On the other side stands quantum mechanics, the theory of the very small, where particles are probabilistic waves and forces are exchanged in discrete packets. These two pillars are spectacularly successful in their own domains, but they are written in completely different mathematical languages, and they violently disagree on what happens in places of extreme gravity, like the center of a black hole. This is the problem of quantum gravity, the holy grail of modern physics. We lack a single theory that can describe how gravity works when space-time is curved down to the tiniest quantum scales. And this is where gravastars become far more than just an alternative. They are a concrete proposal, a detailed blueprint for what such a union might look like in the real world. Their entire architecture is a marriage of the two theories. The smooth, warped space-time of the shell and its immense pull come straight from general relativity. But that exotic dark energy core, that Bose-Einstein condensate of the vacuum, that is a purely quantum phenomenon, a phase transition in a quantum field. A gravastar does not just suggest that the two theories can be combined, it shows one possible way they must combine to avoid a cosmic catastrophe. It forces the quantum vacuum to react to intense gravity, and that reaction, in turn, reshapes the gravity itself. They are locked in a self-consistent embrace, so by studying the potential signatures of a gravastar, whether through its shadow, its gravitational wave echoes, or the light from matter striking its surface, we are not just looking for a strange star. We are conducting an experiment in quantum gravity. We are asking the universe to show us in an observable way how it stitches the fabric of the large to the chaos of the small. Finding a gravastar would be like discovering a fossilized handshake between Einstein and the quantum world, a cosmic artifact proving that the two can coexist in a stable, structured form. It would provide a crucial data point, a real-world example against which every proposed theory of quantum gravity, from string theory to loop quantum gravity, must be tested. The darkness at the heart of a gravastar might not be an abyss but a bridge, the very place where the two great stories of our universe finally meet. The shadowy possibility of gravastars has already escaped the pages of theoretical journals and ignited the imaginations of storytellers. While black holes have long been the go-to cosmic menace in science fiction, a new breed of narrative is beginning to explore these stranger, more structured alternatives. They offer a fresh palette of cosmic mystery, one where the unknown is not a void but a place. In novels and films, objects eerily similar to gravastars appear not as endpoints but as gateways. They are ancient megastructures, dormant engines, or dimensional portals disguised as natural phenomena. Their layered nature, a physical shell hiding an exotic interior, provides a perfect plot device. A crew might land on the seemingly solid surface of a dark star, only to discover it is a crust over a realm where physics works differently, a universe in a bottle. This shifts the story from a simple tale of inescapable gravity to one of exploration and discovery. The danger is not just being pulled in, but what happens if you break through. Video games leverage this concept for breathtaking settings. Imagine a game level set on the fragmented shell of a crumbling gravastar, with shards of ultra-dense matter floating in a nebula, while the strange light of the dark energy core bleeds through the cracks, warping gravity in localized patches. It becomes a landscape where the environment itself is the puzzle, where the very laws of motion change from one platform to the next. This narrative potential taps into something deeper than our fear of the abyss. It speaks to our curiosity about what lies behind the curtain. A black hole is a finality, a period at the end of a sentence. A gravastar is a semicolon, a pause that suggests something follows. It transforms the ultimate cosmic trap into a locked door, and every human story loves a locked door because it begs the question, what is the key? This captures the public imagination because it replaces nihilistic emptiness with enigmatic structure. We are drawn to the idea that the darkest spots in the galaxy might not be endings but containers holding secrets rather than erasing them. They become the perfect celestial MacGuffin, an object of immense power whose true nature is the mystery driving the entire plot. Whether as a gateway to another time, a prison for a forgotten god, or the egg of a new universe, the Gravastar in fiction allows us to play with the most profound questions of reality, all while giving them a solid, if utterly alien, surface to stand on. The elegance of the Gravastar model is undeniable, but in the rigorous world of theoretical physics, elegance alone is not enough. For every scientist captivated by its promise, another raises a formidable list of objections. The most fundamental criticism is a challenge to its very mathematical integrity. Critics argue that the proposed equations for a stable gravastar often rely on what they call exotic matter, a substance that violates one or more of the standard energy conditions. These conditions are bedrock principles in general relativity that describe how matter and energy should behave. Normal matter has positive energy density and positive pressure. But to achieve the perfect balance within a gravastar's shell, some models require matter with negative pressure or even negative energy density. This is not just unusual, it is something we have never observed in a stable, concentrated form. While quantum fields can exhibit these properties in fleeting, microscopic instances, scaling them up to form the entire shell of a star-sized object is a monumental leap. Skeptics see this as a mathematical trick, a way to force the equations to work by inserting a hypothetical ingredient that may not exist in nature. It is akin to designing a beautiful bridge on paper, but realizing it can only stand if its main support beams are made of a material that defies the laws of tension and compression. This ties directly into a second, powerful argument from the critics, the principle of Occam's razor. This philosophical guideline suggests that when faced with competing explanations for a phenomenon, the simpler one is usually preferable. Black holes, for all their paradoxes, emerge naturally and almost inevitably from Einstein's equations. They are a stark, minimalist solution, gravity's simplest answer to the death of a massive star. A gravastar, by comparison, is an incredibly complex construct. It requires a specific phase transition of the quantum vacuum, the formation of a perfectly uniform shell of exotic matter, and a precarious balance of forces that must hold for billions of years. Critics contend that this adds layers of unnecessary complication to explain observations that a black hole already explains perfectly well. Why invent a fantastically intricate cosmic egg, they ask, when a simpler pit does the same job from our distant viewpoint? They argue that the drive to resolve the information paradox and eliminate the singularity is noble, but it should not lead us to propose objects that are more mathematically contrived than the problems they aim to solve. In their view, the quest for a more complete theory of quantum gravity might yield a different resolution to black hole paradoxes, one that doesn't require such a baroque alternative. Perhaps the most damning criticism from a practical standpoint is the stability issue we touched on earlier. Even if you could somehow assemble a gravastar, could it last? Detailed mathematical analyses often show that the proposed equilibrium is dynamically unstable. This means that the slightest disturbance, a passing star's gravity, an infalling asteroid, or even its own quantum fluctuations, would not cause it to wobble gently back to center. Instead, it would trigger a runaway effect. A tiny compression of the shell would increase the gravitational pull at that spot, causing it to compress further, leading to a catastrophic collapse into a black hole. Conversely, a tiny expansion might reduce the pressure, allowing the dark energy core to push harder, leading to a runaway expansion and dissolution. Many models suggest that a stable gravastar configuration is not a robust valley in the landscape of physics, but a razor-thin mountain ridge, an infinitely precise balance that any real-world event would instantly topple. To critics, this makes gravastars a mathematical curiosity, a fleeting what-if in the equations rather than a viable endpoint for stellar evolution that could actually populate our universe. Proponents of the gravastar model, of course, are not silent in the face of these challenges. Their counter-arguments often reframe the criticisms as signs of progress, not failure. They acknowledge the exotic matter problem but point out that our understanding of quantum field theory in extreme conditions is incomplete. The vacuum energy that drives the acceleration of the universe is, in a sense, a form of exotic energy on a cosmic scale. They argue that labeling something exotic simply means it lies outside our current laboratory experience, not that it is forbidden by physics. The instability analyses they contend often depend on simplifying assumptions, like treating the shell as a perfect fluid. More sophisticated models that include the solid-like viscous properties of such ultra-dense matter might reveal new stabilizing mechanisms. As for Occam's razor, they offer a compelling reversal. They argue that a black hole only seems simple because it hides its infinite complexity behind an event horizon. The singularity is not simplicity, it is an admission of ignorance, a place where our laws break down. A gravastar, by contrast, attempts to describe a complete, finite physical system where all known laws remain valid, which is truly the more complex proposition, a finite object described by consistent physics or an infinite breakdown we are forbidden from seeing. This debate is not about right and wrong, but about direction. It is the sound of science working, of two compelling visions of reality being stress-tested against logic, mathematics, and the ultimate judge, the cosmos itself. So the debate remains unresolved, a beautiful theory caught in the crossfire of equations. But science does not end with debate, it begins there. The next chapter for gravastars is not about winning arguments on paper, but about confronting the cold, hard light of the cosmos. Proving or disproving their existence will require a three-pronged assault, combining sharper eyes, more sensitive ears, and more powerful digital minds. Our first window is light, and a new generation of telescopes is preparing to peer deeper into the shadows. The next iteration of the Event Horizon Telescope aims to move from a blurry snapshot to a high-definition movie. By adding more radio dishes around the globe and observing at higher frequencies, it will achieve an angular resolution so fine it could, in principle, read a newspaper on the moon from Earth. This incredible sharpness is not for reading headlines, but for scrutinizing the very edge of the black hole shadow. Scientists will search for the faintest glimmer of light clinging to that dark circle, a potential signature of a physical surface. They will analyze the intricate patterns within the bright photon ring, looking for subtle asymmetries or extra rings that a black hole's perfect event horizon should not produce. Any deviation from the clean, smooth predictions of general relativity would send shockwaves through astrophysics, potentially pointing toward a structured object like a gravastar. Alongside this, space-based X-ray observatories will listen for the final cries of matter. If gas and dust are striking a solid shell rather than vanishing silently behind an event horizon, the collision should produce a distinct high-energy fingerprint, a specific pattern of X-rays just before the material is assimilated. Finding that signature would be like hearing the difference between a stone dropped into a bottomless well and a stone hitting a titanium floor at the bottom of a very deep shaft. The sound is different, and we are building the instruments to hear it. Our second window is not light, but the vibrations of space-time itself. The current generation of gravitational wave detectors, LIGO and Virgo, have opened our ears to the universe. But to hear the whispers of a gravastar, we need to listen more carefully. Upcoming observatories like the space-based LISA mission will detect gravitational waves at much lower frequencies, sensitive to the mergers of supermassive objects. More advanced ground-based detectors with even greater sensitivity will capture the collisions of smaller stellar mass objects in exquisite detail. The key is in the ring down, the final moments after two objects merge. For a black hole, this is a quick, clean fade. For a gravastar, the ringing shell should produce gravitational wave echoes, faint, repeating pulses following the main crash. Detecting these echoes is the holy grail of this search. It would be direct, dynamical evidence of a surface. Researchers are already developing sophisticated data analysis techniques, like AI-powered algorithms, to sift through the noisy data from these detectors, hunting for these ghostly reverberations that could betray a gravastar's true nature. A single, clear echo would be more convincing than 1,000 theoretical papers. The final battlefield is not in space, but inside the world's most powerful supercomputers. Theoretical models of gravastars are complex, balancing quantum fields against curved space-time. To truly test their stability and predict their observable signatures, we need to simulate their entire life cycle, from formation in a collapsing star to their eventual evaporation or merger. These are not simple calculations. They require solving Einstein's equations of general relativity, coupled with the equations of quantum field theory in extreme dynamic conditions. Supercomputers allow us to run these simulations to see if a gravastar once formed can survive the turbulent aftermath of a supernova, or if it inevitably collapses within microseconds. We can simulate the collision of two gravastars in exquisite detail, predicting the exact gravitational wave signal and the flash of light such an event would produce. These digital experiments create a library of possible signatures, a what to look for guide for our telescopes and wave detectors. If our observations ever match one of these highly specific, simulated predictions, the case for gravastars would become extraordinarily strong. This three-pronged approach turns a philosophical idea into a testable hypothesis. We are no longer just asking if gravastars could exist. We are building the tools to go out and look for them, to listen for them, and to simulate them into being. The darkness at the center of our galaxy may hold its secret for a little while longer, but an entire arsenal of human ingenuity is now taking aim, ready to illuminate the truth. Proof of a gravastar would be far more than the discovery of a new type of star. It would be a crack in the foundation of our cosmic reality, forcing us to rewrite the story of the universe from its most dramatic chapters. The first casualty of this revolution would be our understanding of stellar death itself. For decades, the collapse of a massive star has been a tale with two possible endings, a neutron star or a black hole, both defined by gravity's ultimate victory. A gravastar introduces a third, stranger finale, one where gravity is not the sole author. It suggests that in its final moments, a star does not simply surrender to collapse, but triggers a quantum rebellion within the vacuum of space. Death becomes not an end, but a transformation into something structured and stable, where the corpse of the star is the shell, and its new heart is made of repulsive energy. This redefines the life cycle of the most massive objects in the cosmos, turning them from tragic endpoints into potential catalysts for new physics. This single shift would send shockwaves through our comprehension of space-time. Einstein described gravity as the curvature of a smooth, continuous fabric. Black holes stretch this fabric into an infinitely deep pit, but a gravastar proposes that space-time, under enough strain, does not tear. Instead, it undergoes a phase change. The interior of a gravastar is not just curved space, it is space in a different state altogether, a Bose-Einstein condensate. This means the fabric of reality itself has different phases, like ice, water, and steam. The universe could be filled with pockets where space has frozen into this exotic form, held within the shells of dead stars. It transforms space-time from a passive stage upon which matter acts into an active, dynamic substance that can change its very nature under pressure. We would have to stop thinking of gravity as merely geometry and start seeing it as a force that can literally crystallize the vacuum. Perhaps the most staggering connection would be to the greatest mystery in modern cosmology: dark energy. If gravastars are real, their cores are made of the same repulsive vacuum energy that is accelerating the expansion of the entire universe. This creates a breathtaking symmetry. The force that governs the large-scale fate of everything, pushing galaxies apart, is also the force that prevents the most massive stellar corpses from collapsing. Dark energy would no longer be just a diffuse background phenomenon. It would be a tangible building material, concentrated and contained within gravitational furnaces. This could provide our first laboratory for studying dark energy, albeit a distant and extreme one. By observing how these cores behave under the immense pressure of a stellar mass shell, we might finally glean clues about the nature of this force that shapes the destiny of the cosmos. The microcosm and the macrocosm would be linked by the same strange ingredient. Ultimately, the discovery of a gravastar would force a fundamental rewrite of the rulebook. Our two great theories, general relativity and quantum mechanics, have been locked in a Cold War for a century, with black holes as the battlefield. A gravastar offers a peace treaty. It is a concrete blueprint showing how the smooth geometry of relativity and the probabilistic weirdness of quantum fields can combine to produce a stable, physical object. It suggests that the quest for a theory of quantum gravity is not just about reconciling abstract equations, but about describing real structures that might actually exist in the night sky. Finding one would prove that the universe prefers elegant solutions to paradoxes, that it finds ways to avoid its own mathematical breakdowns. We would have to accept that the darkest spots in our telescopes are not abysses, but perhaps the most sophisticated and mysterious objects in existence, cosmic eggs where the laws of physics are woven together into a form we are only beginning to dream of. This journey into the heart of theoretical stars is far more than an academic puzzle. It speaks to a fundamental human urge, the need to look into the darkness and not just fear it, but to understand it. We are a species built to explore, to question the boundaries of what we know, and the gravastar is a brilliant flare sent up from the frontier of that knowledge. It reminds us that the cosmos is not a static painting, but a living mystery, and our understanding of it is a story still being written with us as the authors. Every time we propose an idea as radical as a gravastar, we are not just solving equations, we are expanding the realm of the possible. This relentless push against the unknown is what drives progress, not just in astronomy, but in every field of human endeavor. The technologies we invent to test these theories, from the impossibly precise lasers of gravitational wave detectors to the planet-spanning virtual telescope of the Event Horizon Telescope, become gifts to all of science. They spin off into medicine, communications, and computing, creating tools that improve lives in ways we never initially imagined. The quest to peer at a dark spot in the data forces us to build a sharper lens, and that sharper lens lets us see everything else more clearly. Beyond the gadgets and the algorithms, this pursuit lights a fire in the minds of the next generation. A child who learns that scientists are debating whether the darkest things in space are holes or eggs is not just learning a fact, they are being handed a key. They are being shown that the universe is still strange, that big questions remain, and that they, too, could be the one to find an answer. That spark of inspiration is how we ensure the story continues, how we raise future engineers, programmers, and dreamers who will build the instruments and craft the theories we cannot yet conceive. Ultimately, this deep cosmic curiosity redefines our place in the grand scheme. To realize that we might be on the verge of distinguishing a bottomless pit from a structured object billions of light years away is a profound testament to human ingenuity. It grounds our daily lives in a breathtaking cosmic context, connecting the spark of a single questioning mind to the fate of collapsing stars. Whether gravastars exist or not, the very act of searching for them enriches our collective imagination, reminding us that we are not just inhabitants of the universe, but its conscious participants, striving to read its deepest secrets written in the language of gravity, light, and quantum possibility. So we stand at the edge of a cosmic choice between the infinite pit and the impossible egg. Our journey began with the screaming paradoxes of black holes, those points where physics itself seems to break down. We saw how the singularity and the information loss problem are not just gaps, but fundamental contradictions in our story of reality. From that crisis of understanding, the gravastar emerged not as a rejection of Einstein, but as an attempt at completion. It offers a structured, elegant alternative, replacing a void with a layered object, banishing the singularity with a bubble of dark energy, and trading the event horizon for an ultra-dense shell. This single idea holds the potential to resolve our greatest theoretical headaches, to weave together gravity and quantum mechanics into a stable, physical form. Yet for all its promise, the gravastar faces immense challenges, from the need for exotic matter to the fierce debate over its stability. It remains a brilliant hypothesis, a compelling what-if written in the language of mathematics, awaiting its verdict from the cosmos itself. The telescopes are pointing, the detectors are listening, and the supercomputers are simulating. The evidence, when it comes, will not arrive with a shout, but with a whisper, a subtle distortion in a gravitational wave, a faint extra ring of light, a signature in data that says the universe chose the more intricate, more elegant solution. Until that moment, the mystery belongs to all of us. Stay curious, follow the new discoveries as they unfold, and remember that every time we look up at the dark sky, we are not just seeing emptiness, we are seeing a question. What do you think lies within that darkness, a bottomless pit or a cosmic egg? Share your thoughts on these grand mysteries in the comments below.